Hello, welcome back to Math 332 Linear Algebra. Today we are going to look at one of the application of diagonalizations process used in solving a system of differential equations. So this is a system of differential equations which we want to solve today. But before we do that, just some quick remark on differential equations. So on a lot of situations, it is easier to write down an equation involving derivatives. So for example, Newton's second law says that F is equal to ma, and this is actually a differential equations because F is equal to m times the second derivative of the distance functions, right? So in a lot of mathematical model, in science, engineering, and basically everything else, it is actually way more easier to write down a mathematical equations involving derivatives. So this is equations, mathematical equation involving derivative, and that is the name of the differential equation. So differential equation is nothing but equations involving derivatives. So, but this is not what we want. Most of the time, we don't want to know this. We want to instead know what is the distance with respect to time. So converting a differential equations to this equations, to this variable functions, this is known as solving differential equations. So starting from here to get to here, this is solving differential equations. Okay, now we are doing something more sophisticated today because we are not only solving one differential equation, instead we are solving three differential equations. So we are solving system of differential equations, and this kind of system of differential equations is also difficult in the sense that they are interrelated. So you can see these are what we call the variable functions. So these are not just variable, okay? These are variable functions. These are actually functions with respect to time. And you can see that the derivative, dx1, involves x2 and also involve x3. So dx1 is connected with x2 and x3. So this is equations that is not entirely in the derivative in variable x1. So this is the derivative dx1, but it involves some other functions x2 and x3. So same. If you look at the second equations, the dx2 dt involve variable like x1, involve variable like x3. And the third equation, dx3 here, involve variable x1 and x2. So you can see they're interconnected. So this is what we call a couple system, a system that's coupled together with x1, x2, and x3. Now, if you want to look at a mathematical model that actually can give rise to a differential equation, a system of differential equation like this, you can look at mixing problem. So especially for those people who have taken math 252, you will see that you have a mixing problem that's like this, interconnected mixing problem. This kind of mixing problems will give rise to a system of differential equation pretty naturally. So because this is not a course in differential equation, so we're not going to talk about all this. It's just like some quick remark on what differential equation means. But now we are going to concentrate more on how to solve this. So again, for people who have taken Math 252, you have solved this kind of system of differential equation before, but you might not know the rationale. In fact, you didn't know the rationale. You've just been told to like, hey, convert this into a matrix form, and then look at this matrix, find the eigenvectors and eigenvalue, and if your eigenvectors and eigenvalue is like this, then you can put the final solution in this particular form. And that's it. You've never been told why this is true and how that thing works. And here in this video, in this course in this linear algebra, not differential equations. Come on, Kia, get your act together. Okay, anyway, so we are going to show you why the method works, okay? This is not just telling you what to do, but like, hey, why is this method that you learn in Math 252 works? Okay, anyway, let's get back to this. So first steps in solving a system of differential equation is to put it into a matrix form. So we are taking the variable x1, x2, x3. These are, again, not just variable. It's a variable functions, and we'll put it as a column, okay? And we call this column vectors xt. And so this is xt, this is the column vectors. And for people who are taking Calc 3, in fact, Calc 3 is a prerequisite for this course, which you can take it concurrently. But you already know from very early beginning of the semesters that if you have a variable vectors like this is called vector value functions. This is the functions, right? So this is the functions, and you have a function in this form in R3. The way you take derivative is you take it component-wise, right? So the x prime, we can take the derivative of this column vectors, and the way you do it is you take the derivative component-wise. So you take the derivative component-wise, and that is what this thing means. So if you can see, dx1 equal to this is the same as dx1 equals to this times this. So it's very easy to observe that this system of differential equation can be encoded into this matrix form, where we call this coefficient matrix A. So we call this matrix A, right? So this is our matrix A, this is our matrix big X, and this is our matrix big X prime. Now, so just like in Math 252, the first steps in solving a system of differential equation like this is to look at the matrix A and try to diagonalize it. They didn't say diagonalize it. They never say diagonalize it in Math 252. But what they tell you to do is that once you have this matrix A, you will have to find the eigenvalue and eigenvectors. So finding the eigenvalue is going to be this, solving this characteristic polynomial. And we have solved it before in the previous note. So you refer to the previous computations. You will get lambda equals to -1 and lambda equals to 2. And in fact, lambda equals to 1 will give you 2 independent eigenvectors. So using the terminology from the previous video, this actually give you, if you actually compute the characteristic polynomial, lambda equals to -1 have algebraic multiplicity 2 and also have geometric multiplicity 2 because the eigenspace is spanned by these 2 independent eigenvectors. So this lambda equal to 2 have algebraic multiplicity 1 and geometric multiplicity 1, and that's the the basis. You can take this as the basis for this eigenspace. And so from previous video, we know that geometric multiplicity and algebraic multiplicity matches. Algebraic multiplicity and geometric multiplicity matches. So we know that the matrix A is actually diagonalizable. So it is diagonalizable. We have enough eigenvectors, independent eigenvectors, to diagonalize it. And from the previous video, you know that the way to diagonalize it is to have to come up with the matrix P and the matrix D. And the way we come up with the matrix P is to place all these column vectors, okay, all these eigenvectors as the column of P, as the column of P, and as a column of P. And if you place it like that, then your D, your diagonal matrix, will be consist of the eigenvalue for this eigenvectors, eigenvalue for this eigenvectors. So you have lambda equal to -1, lambda equal to -1, and lambda equal to 2 right here. So as you can see, we can construct this matrix P and D so that your matrix A can be written as P inverse AP equals to D. So that's the key step. Okay, so this is the key step of using eigenvectors. So you use your eigenvectors and eigenvalue to write A and D interconnected like this. So you're writing P inverse AP equals to D. All right, so far, that's nothing to do with differential equations. We are just looking at matrix A and try to diagonalize it. Now, the key steps in solving this system of differential equations using the diagonal matrix is to do a change of variable. So this is a change of variable. This is a change of variables that is critical. So now you want to introduce variable y. So you want to introduce variable y, and the variable y that you introduce has to be interconnected with the variable x in this particular manner. So it has to be x equals to py. So the p is the one that we obtained from above using the eigenvectors as this column. And then this is a change of variable. We want to do this. You will see in a minute so why we are going to do that. Now, if you write everything down, you will see that here, this is a matrix consists of just numbers. And here, these are functions. This is an xt function. This is a yt function that looks exactly like this. So if you take the derivative, you will see that the derivative of this is the same as p times the derivative of this. Okay, p is just like a constant. Okay, a constant matrix. So you would not have to take derivative with respects to t for the matrix P. If you are not clear why this is true, okay, if you are not clear why this is true, you can also just write everything out from this matrix. You can just write everything out, multiply everything out, you will get this. Okay, and then take the derivative. And then you take the derivative, you get this, and you write it back in terms of matrix form, you will see that your x prime will be equals to py prime. So there are two different ways to see it. You can write everything out. Okay, write everything out in x equal to py and take the derivative right here, as you know how to do it usually, right? So you take the derivative here, and you will see that the derivative are interconnected like this. Okay, so that's the key. So you do a change of variable. You do a change of variable, which gets you into this part. And then once you get into this part, now we are going to write the original equations, which is x prime equals to ax, into this form. So remember, x prime now is py prime. So x prime here is py prime, and your x here is py. So rewrite x is py and x prime is py prime. Then you get into this equation. And we don't want to write the equation like this. We want to invert our p. Our p is invertible, so we invert our p. So invert our p and write, so py prime, right? Invert our p. So multiply p inverse here. Multiply p inverse here, right? So this is what you get. You invert the p. That is what you have. And now this is the key. P inverse AP. P inverse AP right here is our D, right? P inverse AP is our D. That's diagonalization process. This is how you diagonalize matrix A. So P inverse AP is equal to D. So now your system of equations is y prime equals to dy. So now you have y prime is equals to dy. And this is key. This is big. This is big steps. The reason why this is a big step is that now all the variable in y are completely decoupled. They are decoupled. Let me say that again. This is what we call a coupled system where the variable are interconnected. Now, I'm claiming that with this, all the y variable are decoupled, which means that they have no relationship among each other. So y1 prime, for example, is -1 of y1, 0 of y2, and 0 of y3. So you can see that y1 prime is only related to the y1 functions. y2 prime is also only related to the y2 functions. And y3 prime is only related to the y3 functions, which means that now we have a very simple system of equation which everyone know how to solve, because this kind of system of differential equations, this kind of equations, dy1 dt equals to -y1. This is what we call separable differential equations, where you do this. You move all the x, all the y in one side and all the t in one side, and you integrate. So solving this is a Calc 1 differential equation problem. The easiest differential equation to solve is what we call the separable differential equations, which is differential equation of this form. So if you solve it, you will get y1 equal to this. Same thing, if you solve for y2, you get to this. And if you solve for y3, you will get to this. Meaning that now we have solved this completely decoupled system. This is a completely decoupled system. They are easy to solve because they are decoupled. They are not interconnected. So we have y1, y2, and y3. We found the answers. They all looks like this. Okay, so this is a y. We solved for y already. We know y. But again, this system is a system of a differential equation in variable x. So we will have to bring back our x. So that's our steps where we bring back our x. So recall the change of variable relationship between x and y. So x is this, p is this, y is this. So now we know the y. So let's put the y here. Now, this matrix multiplications, using the property of matrix multiplication, you can see that this is like this number multiplied this column. So you write it down. Like I'm saying, this matrix multiplications, you can do the usual matrix multiplication, or you can use the insights that we obtained long time ago, first week of class, that if you multiply matrix like this, one way to see it is to take this number, multiply this column, which is given right here. Take this numbers, multiply this column, which is given like this. Take this number and multiply this column, and it will give you something like that. And in fact, you will write your x, okay, your solution for your x, your solution for the x in the form of constants, multiply this vectors, multiply this numbers, constants, multiply this vector, multiply this number, and so on and so forth. And in fact, you can see that this column vector is actually the eigenvectors. This column vectors is actually the eigenvectors. This column vectors is actually the eigenvectors. And right here, you have lambda times t. Lambda is your eigenvalue, so your eigenvalue is -1. Eigenvalue is -1. Your eigenvalue is 2. So in general, if you recall in Math 252, in general, the solution for these differential equations will be some kind of constant times the eigenvector, right? And then e raised to the power of the eigenvalue, t, and then plus, okay, second constant, second eigenvectors, e to the power of the second eigenvalue plus lambda t, and then plus k3, okay, another constant, the eigenvectors, e raised to the power of the corresponding eigenvalue, and you will have the answers that looks like that. And this is exactly what we have. And how do we get this? We got it from diagonalization process. We use diagonalization process critically right here to completely decouple the system. So diagonalization process help us to decouple the system. This is a system that is too difficult to solve because they have all the interrelationship. All the variable x1, x2, and x3 are interrelated. But with this change of variable. This change of variable is critically involved the diagonalization process, because the P here is exactly the same P that diagonalized matrix A. So once you have that, you can see that you completely decouple this differential equation. The system of differential equations is now completely decoupled, which is so easy to solve. Solve the decoupled system, and then write it back, reconnect it back to the x variable, and you'll see your answers looks like this. And this is why in Math 252 differential equations, when you learn how to solve the system of differential equation at the end of semester, you will see instructions for you to write down your answers like that. And that's the reason why, because you diagonalize the matrix A and you decouple the system, solve for the decoupled system, and then write back so that you relate back to the x variable. And how cool is that? Right, so this is the video on how to apply eigenvectors and eigenvalue to solve a system of differential equations. The next video, we'll look at how we're going to solve another type of equations, which is called the difference equations. So difference equations is not like differential equations. It's some type of equations that involve the difference. Okay, so we'll look at that in a minute. And this is the end of this video. Thank you very much.